in this segment we're going to take an example of Euler's method. So Euler method is the first method when we talk about the solution of ODEs, and let's go and take an examples of Euler method. So somebody gives me a differential equation of dy by dx plus 0.4y equals to 3e power minus x. What they ask me to do is calculate the value of y at x is equal to 3 and gives me an initial value that y sub 1 y sub 0 is equal to 5. But eventually when we talk about when we see the differential equation, we solve the dependent variable with respect to x. So in this question, to ask to find about the value of y at x is equal to 3. So I choose step size of 1.5. Uh, this is the initial value where I am at, and it's when I step when I step out, um, I able to calculate the value of 1.5 or value of y at 1.5, and when I second step out, I able to calculate the value of y at x3. This is our goal where we want to calculate the value of y at x is equal to 3. So in this step when we looking about looking into a differential equation, then we have rewrite our equation in a particular form of dy by dx is equals to f of x comma y. By keeping the value by just keeping the point 0.4y to the right hand side. So this is our function 3e power minus x minus 0.4y. I'm just separately writing my function, which is my slope equals to 3e power minus x minus 0.4y. So this is the formula of Euler's method. yi plus 1 is equals to yi plus f of xi comma yi the step size h. So in the first iteration we calculate the we take a I equal to 0, and it will become a y1 equals to y naught plus f of x naught comma y naught s h. In this question, in this question in the initial condition, we have x naught is 0 and y naught is 5 and a step size of 1.5. So here is the values at value x naught is 0, y naught is 5 and h is 1.5. To put this value in the formula to calculate the first y1, so y naught is 5 plus f of function of the value of function at 0 and comma y 5 and the step size 1.5. So 5 plus the function will become a 3e or minus 0 minus 0.4y and to value of y, which is 5, into 1.5. This value turns out to be 1, and multiplied by 1.5, this gives me a value of 6.5. So this is the approximate value of y1 at x is equal to 1.5. X is equal to x naught plus h, and x naught is 0 and h is 1.5, then x1 will become 1.5. So we go to the further step. Now we calculate the value at I is equal to 1. Then it will become y2 is equal to y1 plus f of x1 y1 and step size h. Now we calculate calculate this step on the behalf of x1 and y1. Now our x1 is 1.5 and corresponding y1 is 6.5 and h is 1.5 again. It will be constant. So y2, put this value in this equation, it become y1 is 6.5 plus function value of function is 1.5 and 6.5 and the step size 1.5. Please keep in your mind that this is the value of y, approximate value, not exact value. This is the value of y at 1.5. So put these two values in the function, 3 e power minus 1.5 minus zero point 0.4 into 6.5 and 1.5 into multiplied by 1.5 step size, which is a step size. Then this value turns out to be minus 1.930461, and the whole answer will become 3.604. So this is the approximate value at x2, and x2 will become a 3. So we will able to calculate the value of y2, which is y2 at x2. X2 is 3, and we know x2 is 3. So let's calculate the true error by first we calculate the true value of 3 at uh, true value of y at x is equal to 3, which is 2.763. So we will able to find the true error by subtracting the approximate subtracting the approximate value. So which is true, the real value will become minus 0.841, and the absolute true error will is 30.44%. So it's gives me an idea that as we take a smaller value, as much as smaller value of high step size, it will give a smaller error. Okay, thank you.